Two. Okay, perfect. So, well, then let me welcome Wolfgang Spitzer from the Fern-Universität Hagen. So I'm very happy that you are here, unfortunately only online, but of course there's nothing we can do right now. And we are very much looking forward to your talk on entanglement entropy of the ideal Fermi game.
Okay, thank you, Felix. Thanks for the introduction and the opportunity to speak here. So I have a number of transparencies. I can send you the PDF file in the end, but maybe I can only cover half of it. So, and you are welcome to interrupt me at any time. This is all I'm going to talk about is joint work with Hajo Leszke and Alexander Sobolev over the years, and I will give you a large fraction of our joint work. As to the introduction of entanglement entropy, I will abbreviate this with EE. And this concept of entanglement entropy is a much studied concept, mostly in condensed matter physics and quantum information theory. It was not introduced by this community, but rather by astrophysicists in the mid-80s, and then independently again in the early 90s to explain Bekenstein-Hawking entropy of black holes. Here in this context, the entropy of a black hole grows with the surface area rather than with the volume as we are used in usual thermodynamics. I have to stress that entanglement entropy is a purely quantum mechanical effect, so there is no counterpart in classical mechanics. So the thing about entanglement is that you may have complete information on a given system. So this will be the equilibrium state of the infinite volume system. But you have less information on a subsystem. So the entropy can grow if you go to a subsystem. And something like this does not happen in classical mechanics. If you have full information on a system, like you know all velocities and all positions of the particles, I mean, you know everything about a subsystem. So this is a purely quantum mechanical effect. So we are.
Wir sprechen weiter über Integration, wie man Residuenkalkül anwenden kann.
Excuse me? I did not catch the question. I mean, acoustically.
So I think this was just a problem with the audio, so don't worry. Just
okay.
We can hear you very well.
Okay. So I mean, there is maybe many concepts of entanglement entropy. We are interested in spatial entanglement entropy when we localize to a domain, to a spatial domain in RD. I will come to that more concretely. I mean, there is a large body of results in condensed matter physics, and this is mostly numerics. And some of it is conjectural, and one has to say that there is rather few rigorous results. In recent years, there has been a growing number of rigorous results. And I want to deal with the ideal Fermi gas in an equilibrium state. So an equilibrium state. So there's at least so ideal means here. I mean, there is no pair interaction between the particles. So there is possibly an external field, like an electric field or a magnetic field. But the fermions are non-interacting, pairwise non-interacting. And the fermions, they reside in Euclidean space, usually Euclidean space RD, D is the dimension. And an equilibrium state is at least, I mean, is determined by parameters. So this is on the one hand, it's the temperature, so that's capital T, and if T is equal to 0, I call, or one calls an equilibrium state a ground state. So ground state is the same as equilibrium state at temperature equal to 0. So there is the parameter capital T, temperature, and there is a second parameter that characterizes the equilibrium state. Either in the grand canonical ensemble or description, you have what is called mu. It's called the chemical potential. It's not a potential, it's just a number. It's a real number. So that's the mu in R. Or in another description of the Fermi gas, it's the temperature plus the particle density rho. And you can go from one to the other, which I will not go into, but this is standard statistical mechanics, how to go from one to the other. I mean, it's, yeah, that's one thing. In all cases, I will just denote an equilibrium state here by omega sub t. So omega is an equilibrium state, and the lower index t is the temperature, and you either think of the density rho, or you think of the chemical potential as an additional parameter that characterizes these states. For the entanglement entropy, there was a result there was a result in 2005. I will come to that, and this was published in FISREF letter. There was no proof, but there was a very nice correspondence they realized, and we proved that mathematical statement in some years ago. At positive temperature, our asymptotic result is also new. I mean, it's new and also new in the physics literature. It's rather complicated. I mean, this term is rather complicated, so you cannot easily guess this from physical considerations. So that's why it was not known. If I have the chance, but probably not, I will also report on our result for the entanglement entropy of the ideal Fermi gas in two-dimensional Euclidean space with a constant magnetic field. So for that, there were some results, say 10 years ago, but only proved recently, and we have an extension to that also. But maybe I will not come to that. So that's at least the plan. And now I will go more into details. So in this talk, lambda will be a bounded Borel set in RD. I mean, there will be more specifications about the smoothness of the boundary, but for the moment, lambda is some bounded set. And we will localize, or you can also say reduce or restrict, the equilibrium state, omega sub t, to this lambda. And this localized state, I will come to that, how this is done, but this localized state I will call omega sub t for the equilibrium state, restricted to lambda. I will say how this is done, but that's the notation. And the local entropy is the von Neumann entropy of this localized state. Okay, and that entropy will be denoted by capital S. It depends on the equilibrium state or whatever state, and restricted spatially to lambda. Well, you have the big one and you restrict it to some lambda. However, this is done. And the entanglement entropy, or sometimes also called mutual information, is another entropy that measures somehow the correlation of the particle inside with those outside lambda. And so the outside lambda, that's lambda complement, it's RD z minus lambda. So loosely speaking, and that's why I have here quotation marks, I define the entanglement entropy, say of the equilibrium state localized to lambda, as the entropy of the state localized to lambda plus, and that's the second term, plus the entropy of the state localized to its complement. And I subtract here the entropy of the overall state, right? So this restriction is not needed. I mean, this is the initial equilibrium state on all of RD. Okay, so the problem with this, so why do I put here quotation marks? Because usually these last two entropies are infinite. I mean, there's an infinite amount of entropy in the infinite volume state at positive temperature. So, but there is a way to make this a well-defined definition. At t equal to 0, there is something special. At t equal to 0, the ground state is actually a pure state. So being a pure state, the entropy is 0. And so that's one thing. So the entropy of the infinite volume state is 0. And the entropy of the second entropy, namely the entropy of the state localized to the complement, happens to be equal to the entropy of the state localized to the domain lambda. So this is special to temperature 0 because we talk about a pure state. In that case, at t equal to 0, the entanglement entropy is just, the entropy of, this part plus, oops. I have to go back. So the entanglement entropy just happens to be twice the local entropy, because these first two terms are the same and the last one is 0. This is particularly for temperature 0, because we start with a pure state. And because of that relation, up to the factor 2, sometimes the local entropy is called the entanglement entropy at temperature 0. Okay, so up to a factor 2, the two things are the same at temperature 0. So yeah, so the concept of local entropy, that is, I don't know, 80 or 90 years old. The concept of entanglement entropy, that's a newer and more fashionable term. So most people use entanglement entropy for the local entropy at temperature 0. There is other measures than these measures, like the logarithmic negativity, but if you allow me, I will not go into that. Okay, so this is still some informal definition, but you should keep that in mind. Our goal is, so what is our goal? I haven't defined it yet, but our goal is to understand these entropies, at least if the domain to which I restrict the state is large, right? And so we fix the state, we localize it to a domain, and we want to grow this domain and see how the entropy behaves. So to this end, we fix the domain and blow it up by a parameter capital L. So I'm interested in the asymptotic behavior of, say, the local entropy of an equilibrium state localized to L times lambda, and L tends to infinity. Okay. So most, if you go to the literature, say condensed matter physics, they mostly deal with ground states. So temperature T is equal to 0. And the interest that has sparked this, or that was in this community is a little surprising logarithmic enhancement in the scaling of the of entropy. But typically at positive temperature, you would see a scaling of the local entropy. So this is in equation 4, S of omega sub t localized to L times lambda. There is a leading term which goes with the volume, right? So that's the volume of the restricted. So that's the lambda times L to the D. The D is the dimension. And there's a prefactor, and the prefactor is the usual thermal entropy density that we know from physics. That's the derivative of the pressure. If you know these things, if you don't, well, it's just a coefficient. Little s of t, it's also called specific entropy. If you know these terms, otherwise it's just a prefactor that depends on the temperature times the volume, and there is a second term. Well, there is a term that has lower order. It's of the order L to the D minus 1, and the prefactor. This prefactor I call eta. It depends on the temperature and on the boundary of my domain to which I restrict, plus lower order terms. That's one thing. And for the entanglement entropy, we don't have this volume term, but it starts with the surface. I mean, it is a surface term. There is a prefactor in front, which is this eta. It happens to be twice this prefactor from the entropy, the second term in the entropy, and goes with L to the D minus 1 plus lower order terms. The first I have explained, the description of this eta term is rather complicated, but it simplifies as t goes to 0. At temperature, so this is for positive temperature. At temperature 0, the scaling is different. There is no leading term, so S of 0 will turn out to be 0. And there is an extra log in front of the L to the D minus 1. So there's an extra log L in front of here. But this depends on the model. It's not universal, but we will see when this comes up and when not. At this point, I would ask the audience if there is anything not clear, because in the rest of this talk it will trying to argue for this for 4 and 5. Is there any question?
Everything seems clear to me, but of course, maybe we should ask the young people.
Yeah. It's not a talk for me. If there is anything unclear with the notation, or should I recall something, there will be definitions of this reduction and so on. Okay, so I will talk about an asymptotic growth of local entropy and entanglement entropy. At temperature 0, they're almost the same except for a factor 2. At positive temperature, you have to, it's different. Okay, so if not, then I will go to the next and be more specific. So we will deal with, as I said, with non-interacting fermions. So what else is there to specify? There is just a one particle Hamiltonian that we have to specify, like the kinetic energy. And that's the first thing. So what is the typical thing? That's the Laplacian. So the Hamiltonian is just a Laplacian on RD. Or more generally, you could have some function of the momentum operator. So capital K of the momentum operator. This capital K is called in physics dispersion relation, but the most important thing is the quadratic one, K of C is equal to C squared, right? But you could have other ones, but that's just I mean, suitable ones, not something crazy, but something polynomially bounded or something like this. The other thing, the story is very different. Is the Landau Hamiltonian. So there we consider, so say in 2 dimension, it's free non-interacting fermions in R2 in a constant magnetic field perpendicular to this plane. and the Hamiltonian is given here by minus, I mean, it's only kinetic energy minus I times the gradient, that's momentum, minus what is called a magnetic gauge field. And there is some choices you can make, but the rotation of A is equal to the magnetic field vector. Okay, so that's another thing. No matter what system you know, no matter what Hamiltonian you consider here, we need the Fermi function. So the Fermi function is this function that so it's a function that you take real values and it goes into the unit interval 0, 1 at positive temperature. So you should think of it's a function like this. Yeah. At positive temperature, it's 1 plus e to the power e divided by temperature inverse. And if you let t down to 0, so this function will get steeper and steeper, and until if you go to t equal to 0, you will hit this step function. So it's the Heaviside step function at the negative half axis. And I introduce what is called the one particle density operators. I mean, this all comes from physics, but it is an operator on the one particle Hilbert space. The one particle Hilbert space is L2 of Rd. So that's where a single fermion resides. It's a single particle Hamiltonian. And this dt, one particle density operator, is you apply the Fermi function to h shifted by mu. So mu is this chemical potential, and this 1 is the identity on L2 of Rd, on this single particle Hilbert space. So written here again, it's 1 divided by 1 plus e to the h minus chemical potential divided by t. Right? So yeah, is that clear? So there is the so this is just on the one particle Hilbert space. Okay, so so this is because we deal with fermions. If you had bosons, there would be a minus. Okay, but this is fermions.
And also, Wolfgang, you don't need to consider spin or anything like that.
Right. So exactly. So I don't consider spin. So this is spinless fermions. Exactly. So that's why I only have L2 of Rd, but you could also have L2 of Rd into CS or whatever. Right. So that's correct. That's correct. So you can even right. Spinless fermions. So no spin component. Right. Okay. So what is the connection between this one particle density operator and the equilibrium state? This one particle density operator determines all the correlations. So if you have seen something like this before, you know what I'm talking about. If you haven't, well, then it's a bit hard to explain. So there is a one particle picture that's we're going to work with. In the back, there is the many particle system, and this is not so easy to describe. But there is something, there is what is called Fermi creation annihilation operators. This is the A star of F or A of G, where the F, the function, is in L2 of Rd, in the one particle Hilbert space, and A star of F, so to say, creates a fermion with wave function F, and the A of G annihilates one. You have to be, well, I cannot explain this in 1 minute, but the equilibrium state, omega sub t, is an equilibrium state on all of, containing all the fermions. And it takes expectation values on this Fermi algebra, which is generated by this A star F and A of G. Right? So this is the left-hand side is the many fermion state, right? And on the right hand, but you can calculate all the correlations. using single particle expectation values. And on the right-hand side, there is only single particle expectation values, namely the scalar product of GI with dt, this one particle density operator, acting on Fj, and you take a determinant of this whole thing, right? It's also gauge invariant because only n equals to m gives a non-zero value, right? So this is the connection between the many fermion state, equilibrium state, and the one particle state. Anything can be computed on the one particle state. Okay. So we're gonna work with the one particle operator because that's much handier than this big thing, right? But this is only possible because we have non-interacting fermions.
Okay, so this means like people in algebraic quantum field theory, they would
right.
state or something like that.
This is the algebra. This is my beloved. This algebraic approach to quantum field theory or to statistical mechanics, I would say. Statistical mechanics. It has the advantage. I mean, you cannot. It's the only approach I know which works for the infinite volume system. With Fock space, you cannot describe this because Fock space you need a finite volume, and you cannot describe it on infinite volume. It's a clean and nice prescription. There is no Fock space. I mean, you can work with Fock space only on finite volume. Okay. Good. We will not work a lot with the Fermi algebra and that stuff. We will only work with the one particle operator. Okay. The operator dt that I introduced here, you see it's this step function or this smeared out step function. This is between 0 and 1. You see the ft goes between 0 and is between 0 and 1. So the dt, I mean, applying ft to a self-adjoint operator will stay between 0 and 1. So this will be an operator between 0 and 1. This is just this inequality, these two inequalities. So the dt for fermions, that's between 0 and 1. And if you had, I don't know, spin, then this 1 would be a 2 or something, but it's bounded. For boson, it's not. It's only positive. Okay? And so this is for positive. So it's always between 0 and 1. But at 0 temperature, it's even a projection. It's a projection operator because you have the Heaviside function. And that is called the Fermi projection. It is the projection up to energy mu. Okay? So at temperature 0, the one particle density operator is a projection called the Fermi projection. So now how does this localization of states on the Fermi algebra work? There is one surprising thing. I mean, this is all known for a long time. If you have a set lambda, it doesn't have to be bounded, but let's take a lambda in Rd and take the Hilbert space of particles that reside in one particle Hilbert space for fermions that reside in this lambda. So this is this H1, L2 of lambda, and you have the other one that reside in the complement. So the overall Hilbert space, the L2 of Rd, is a direct sum of these two. But the Fermi algebras, it's even though they are fermions, I mean they anti-commute. The Fermi algebra is the tensor product of these two Fermi algebras. Having this, you can do the reduction, like in probability theory. It's in probability you say theory in ordinary you call it the marginal state or the partial state. So if you had a state on the big space on the algebra A sub h on the big one, then you can reduce it to some lambda. So omega reduced to lambda, you just take all observables that pertain to the algebra in lambda, right? And you take an observable A and tensor it with the identity on the other space, and just take those expectations. So the one here in this line is the one in this algebra. So that reduces. That is a reduced state on this Fermi algebra. Vice versa, I mean, you can use it to the complement by taking observables in the algebra A sub H2, and you tensor it with the identity on the left space. Okay, so that's as in probability theory. You reduce a state or a measure to the subsystem. The important thing is, what does it mean for the one particle density operator that determines the state? So what is the and that is very simple, namely, so if the omega restricted to lambda is the state, the reduced state as I just defined, then the one particle density operator that goes with the localized is just the density operator and multiplied from the left and right with the indicator in lambda. So this is very simple and very nice. Okay, so in the following sense, that all the correlations, like we had above, all the correlations of this reduced state are determined by this reduced one particle operator. Okay, if I did not have such a description, I wouldn't know how to continue, right? So for the big state, we have a one particle density operator, and also for the localized ones, we have a one particle density operator, and it's very simple. You just take the D and you conjugate it with the indicator on the subset lambda, right? Okay, and now we can define the von Neumann entropy of any quasi-free state, of any state which is determined by a one particle density operator. Namely, I say S of omega or S of D, it's the same. So this is on the many fermion level, this is on the one fermion level. It's just a trace of a certain function applied to D. So first of all, D is an operator on our single particle Hilbert space, and H is a certain function. I will tell you in a second. And then you take the usual Hilbert space trace, the trace on L2 of RD, right? In this case, H is the binary entropy function defined by the following. So H of t, except at the two boundary points, it's H of t is equal to minus t log t minus 1 minus t log 1 minus t. This is because we have fermions. For boson, it's slightly different. But anyway, we are dealing with fermions. Now I'll give you a picture. So this function, I hope you can see. So this is it looks like a very boring function, almost like a polynomial, like a square. Except it is smooth inside, except at the two boundary points, which is quite a technical problem. It's non-smooth because of the logarithm. But this is the function. I cannot explain to you why we use this function. You need to know some statistical mechanics, and to justify this, you would have to go to Fock space and so on. But I cannot tell you this story.
Okay, but maybe just
sure.
You go first, Felix.
Okay, so just a short question, just concerning this derivation. I mean, of course, we can't go to the details, but I mean, is it correct that Neumann entropy computed in the Fock space?
Exactly.
Is the same as one particle?
Exactly. That's how this comes. So exactly. So in the Fock space, you would have a big trace on the Fock space, right? And it's the usual trace of rho ln rho, or minus rho ln rho, where rho is the e to the minus beta h.
I see. Okay.
Okay. So you have to go back to the Fock space, and the usual so the usual for Neumann entropy would be trace of minus rho ln rho.
Yes.
Right on the Fock space, and it translates into the one particle space description by using exactly this function little h.
I see.
And then this comes, and that's how you go to the definition.
I see.
I mean, this is all known. This is nothing from us. This is all known.
Okay, sure.
Okay.
And this works also for positive temperature, so it doesn't.
Yeah. No, I just need this d, right? It's pretty general. So you take any state omega.
Yes.
Any state, quasi-free state, this is called, any state which is determined by a d.
Yes.
I'm not saying this is well defined. You see, I say here it's because the h is positive, and d is because h is positive, take only positive values, and d is some self-adjoint operator, spectral theorem, h of d is also positive, and I don't tell you that the trace is finite. You see, I write here, no, really, this is no, really. So see, I mean, it is a value between 0 and infinity, and it's no exaggeration to say that mostly it's infinite. No, right.
I was actually wondering about the trace of D too, or the trace of D. Would the trace of D correspond to the expectation value of the number of rate of particles?
No,
like the number of occupied?
It's the kernel d of x comma x. That would be the density. That is correct.
So if I have a system with finitely many modes, then the trace of that is the number of particles in the system.
Yeah.
Okay, good. Thank you very much.
Yeah, from D you can compute all this. Right. Yeah. Good. So we have to take this function h as it is. I mean, that describes that describes the physics. So that's the picture. Okay, and the local entropy of any state omega, that is any state omega, that is described or respectively the one particle density operator d. Entropy of omega localized to lambda is the entropy of the reduced state by the previous formula, right? So it is h of applied to d of lambda. Okay. Fine. Let me go back to 1. I cannot use this formula for so this is the local entropy. I cannot use this formula directly so this formula that I go to lambda and then to the complement, and I subtract the overall entropy, because usually that is infinite. So I have to do something. I have to do something else. Namely, I take the operator, which is, well, this first is d. You localize it to omega, and and to the left and to the right. And I subtract another operator, which is, you see, the difference is that I pulled out the indicator from this expression. So here it's h of the restriction, and here the restriction is outside. Okay, so that's the difference. And then I define the entanglement entropy of a state omega localized to lambda as the trace of omega localized to lambda plus the trace, of delta, of this delta, of this difference, of this operator difference, plus the same thing with lambda complement. Okay, so what do I gain by what is called operator concavity? At least this thing here, this combination, is positive as an operator. Fine, just believe me. And in this line, I take a trace. So at least the entanglement entropy is a positive number. Whether it's finite or not, well, in general, maybe not, but in an important case, it will be finite. Okay, so we have something which is at least positive. And now we have to say, when is it a finite number? Okay, I will come to an explanation of why we define it like this. But let me state the following. If we take now an equilibrium state at positive temperature, then we can prove that this operator that we just introduced, this operator here, is trace class. So if we plug in the lambda or the complement, so you see, we don't take the trace of these individual terms, but we take the trace of this regularized combination. And if this omega is infinite, I mean, is the complement of something bounded, we subtract quite a bit. And that makes the whole thing finite. Okay. Anyway, so if we start with an equilibrium state at positive temperature, the entanglement entropy, as I just defined, is well defined. It's a well defined trace class operator, and we even have an a priori estimate. And the a priori estimate is that it is bounded by something, a constant which depends on the domain, times something L to the d minus 1. So this is great. So it looks like what we intend to prove, that entanglement entropy is bounded by the surface area. And the surface area goes with L to the d minus 1. Okay. So this is fine. So this is in 5. Remember, 5 is an expansion for the entanglement entropy. It goes with L to the d minus 1, and there is a prefactor. And what I claim now is we have at least a bound which goes in this direction. I don't tell you how to prove this now, but I tell you that we have something like this. So what's an explanation for defining this entanglement entropy? The entanglement entropy was defined as the trace of this difference of these two deltas. So entanglement is equal to that on the left-hand side. And here I just copied the definition. There is nothing new here. It's the trace of, but you see the parenthesis outside. So this is an identity. I'm just recalling the definition. It's the trace of h of this localized minus the localization outside, plus the other one for the complement, for lambda complement. And you cannot, for the first you can, but for the unbounded domain, you cannot do the trace of the individual terms. But in the second term, the trace, so what is inside is a trace class operator, but not the individual terms. And if you would put these two together and use cyclicity of the trace, you would exactly get that one. Right? So if they were trace class, you would get to S of lambda, to the entropy of the overall state, because these two things add up to 1, these two indicators. Okay, so I'm saying it is a natural definition for entanglement entropy, but you have to be careful how to define it for equilibrium states where you have lots of entropy for the infinite volume state. Okay. You don't have to be that careful for a temperature 0, because you start with a state that has no entropy. Okay. So I want to go back. So here I have a bound on the I have an a priori bound on the on this entanglement entropy, but I haven't determined the precise scaling, right? The precise coefficient. The precise coefficient is this eta, or I called it eta. And to determine this precise coefficient, as I mentioned, this is rather complicated. And I don't know what time it is. I will not. I have two pages to get to this definition, but I will not go through it. Already in dimension 1, you have to do some work and prove that this coefficient is well defined. So here I say it's positive. and it's even worse in higher dimension. But there is a, well, I mean, there's a description for it. So there is a, I'm claiming there is a, this eta coefficient can be computed as an integral of certain symbols, as they are called. It is complicated, and it doesn't help much if I go through this.
Okay, sure. I agree. I mean, let's put it like this. I'm happy to hear that it's not so easy because it doesn't really help if we go through it. So, but I mean, it's so complicated that as a physicist, you would not be able to guess it. And how explicit is what you get as the eta in the end? Yeah. Okay. Okay. It's as I say, it's an integral over the tangent bundle of the boundary, a certain integral. Okay, and this comes from some differential calculus or something like that. Is this? Yes. And it can be simplified in cases, and I would say something about it, but it is quite complicated. Anyway, here is the statement that we proved some years ago in dimension 1 together, and Sobolev did it for higher dimension. So we have a bounded domain. It has to have some conditions, piecewise C1 smooth, finitely magnetically connected components, and so on. And the one particle density operator is as I recall, it's 1 plus e to Hamiltonian shifted by mu divided by the temperature and inverse. That is the one particle density operator of the equilibrium state. Then the trace of the reduced or localized equilibrium state has an asymptotic. So here I just recall the definition. It is this complicated coefficient eta times L to the d minus 1. Okay. So the entanglement entropy was a sum of two terms. So, and for each term you get, for each term you get this eta. I mean, no matter whether you talk about the lambda or its complement, you have the same eta coefficient. That's why in the entanglement entropy, which is sum of two terms, you get 2 times the eta coefficient. And you get also, so if you say I don't care about entanglement entropy, I can tell you that you also get a 2-term expansion of the local entropy. So the local entropy, that's a concept that exists since, I don't know, 80 or 90 years. I will not go through this, but it follows immediately from this theorem. So the local entropy, so entropy of the equilibrium state localized to lambda, is the usual leading volume term, which goes with L to the d times the volume and times this coefficient, which is denoted by little s of t. It's the specific entropy density, thermal entropy density. It can be written down explicitly, but that is known. And the second term, that is new. It follows from this expansion. Okay, so that's what I say here. So that's positive temperature. You have an L to the d minus 1 scaling or area law scaling. At temperature 0, the situation is different. And that's what we proved earlier. So here's the entropy of the ground state. Omega sub 0. The 0 stands for temperature 0. And entropy of d naught. D naught is the one particle density operator at t equal to 0, which is just a Fermi projection. And in this case, it's a bit more general, but the d naught, you should think of the indicator of some Fermi surface, Fermi C, gamma applied to the momentum operator. So it's a bit more general, but that was it. That was it. What is important. So I've copied the definition. So the entropy is the trace of the binary entropy function applied to what operator? Applied to the operator which is the Fermi projection in momentum space,
and the localization is to the left and to the right. Huh? This is all on the one particle level. And the asymptotics goes as follows. There is a two-term asymptotics. There is a leading term of L to the D with a coefficient h of 1 times the product of this volumina, the volume of the localization domain and the volume of the Fermi C. And there is a second term, which is a lot more complicated. There is a certain factor that depends on h, and there is a double surface integral. So this double surface integral is a lot simpler than this eta. And yeah, a certain double surface integral times L to the D minus 1 times a log. Right? At temperature 0, there is an extra log.
Just stupid question. So this logarithm, can I understand intuitively where this comes from? Is this more like an infrared effect or something like that?
Well, it is because you have the sharp Fermi surface.
Okay, so this means in the momentum space, it's like a non-continuous or discontinuous.
Exactly, it's because of the non-continuity. So because of the the other one was very smooth. And if you have a smooth symbol, and now we have a discontinuous symbol, and that's where the logarithm comes from. Such a phenomenon is very well known in Schege asymptotics.
Can I understand this intuitively? If you take the Fourier transform, then in position space, you no longer have rapid decay.
Exactly. Yeah, exactly. That's exactly. The decay is much slower.
Mm-hmm. Okay, good. Thanks a lot.
Sure. Okay. Let's see. There are some remarks to that. So the leading term. So I say there's an h of 1. I mean, the h could be a different function. Doesn't have to be the entropy function. And in our case, entropy function is 0. So there is no volume term. So the leading term, it starts with L to the D minus 1 times log L. Right? At positive temperature, we only had the L to the D minus 1. At temperature 0, we have an extra log. Okay. Oops. And if we have, for example, a nice, so this is exactly what Felix was directing to. That the extra log is because of the step discontinuity of this symbol and the slower decay of the Fourier transform. So you can compute this. I mean, in the standard example, if we had a simple dispersion relation like p squared, then you can compute this double surface integral, and it's the surface area times some complicated expression, but never mind. Okay. The story of this formula. Of this formula is interesting. Namely, so this formula appeared in 2005 in a physics review letter by one mathematician, Gueuf, and a physicist, Glich. And one knew about entanglement, and the other one knew about Widom. Namely, they connected. They saw the connection between entanglement entropy, or this expansion, and the conjecture by Widom from 1982. And so Harold Widom, he was working since the 60s on Schege asymptotics. So Schege asymptotics is mostly about determinants of Toeplitz matrices. And the asymptotic expansion depends very much on the regularity or smoothness of the symbol, as they call it. So our symbol here is the Fermi function, or the step function, and depending on the smoothness, you get a log or you don't. And this formula is, of course, a higher dimensional, and it is a higher dimensional version of a Schege asymptotic, of a formula for Schege asymptotics. So Widom came up with a formula. It was only conjectural, And at the time, Georg and Glich used this conjectural formula to get this to get a conjecture about the entropy. And when I heard about this, formula in a talk of Georg, I was very much interested by this conjecture because I was working previously on asymptotic analysis, and that fascinated me. So Sobolev proved this remarkable conjecture by Widom for smooth functions. The entropy function is not smooth. So in a joint effort, we extended the asymptotics from smooth functions to the entropy function. And this transition from smooth to non-smooth functions, that is heavily based on classical Biermann-Soloniak bounds. And yeah, that's for one thing. Recently, Peter Müller and a student of him, Ruth Schulte, they extended it to other Hamiltonians, not just the Laplacian, but to a Laplacian with a compactly supported potential.
Well, in fact, Peter Müller will give a talk in our seminar in January.
Yeah. So he might speak about this, but he also has another work on the dimer model. So entanglement for a one-dimensional dimer model. So this is I like this. This is also very nice. But using our result as a starting point and saying when you add the V, nothing changes, but you have to prove it. and so which is kind of intuitive. I mean, you studied the large asymptotics, so outside some compactly supported potential or having some decay, it shouldn't matter. And this shouldn't matter, that's what they prove. Okay, so I have presented two results. The result for t equal to 0, where you have a log, an extra log, and I have presented before the L to the D scaling at positive temperature. So say, what have these two things? How can you bridge these two results? So okay, so that's a question I'm interested in, hopefully you, and that is on my next slide. So I repeat, we have an L to the D minus 1 scaling of entropy, whether it's the local or the entanglement, at positive temperature, and we have an extra log at t equal to 0. So how do you fit these two things together? The thing is that the leading volume term of local entropy, that vanishes. I mean, this is known, so that disappears. You don't get any log or anything strange from that term. So that's just gone as you let t down to 0. But this coefficient eta, complicated as it is, it develops it develops a singularity in t. So you can prove that the eta coefficient, as complicated as it is equal to the coefficient that we saw at t equal to 0 up to a log 1 over t, exactly to a log 1 over t. So if you think of 1 over t as L, you would these two, the temperature 0 and the positive temperature result, they fit together. So the next topic on my list would be the Landau Hamiltonian, but I'm happy to stop at this, pause at this point, or go back. It's up to you.
Well, also it's, well, maybe up to the, well, maybe first of all, before deciding, just a naive question here. So does this, that this matches up if 1 over t is equal to L, does this mean that kind of the length scale in position space is typically just 1 over the temperature? Is this somehow the way to understand this?
Well, I mean, we didn't, well, I don't know whether there is some philosophical thoughts or physical physical reasoning for that, or whether you would have expected it. I don't know. I mean, I understand it from a mathematical point of view, and somewhere this, I mean, it doesn't have to, but it happens to agree. If it were t has to be root L, I have no objection. Maybe no, I mean, or if it is e to, I mean, if it's some other combination, I don't have a reasoning why it cannot be any other combination, but it's the simplest possible. But it's to be honest, maybe I have thought about this. It's the simplest possible thing that I can think of, and it just gives the right answer. It could have been more difficult, or more, yeah, it could have been more strange, but it's the simplest possible identification. And you could be right. There could be a more physical explanation.
Okay, good. So I think we still have time. I don't know how long would this magnetic field take?
Well, I can shorten it. I mean, it's so the important thing is I will go to
I think then just go ahead with the talk.
Okay, I'll go ahead. Yeah. So what is more recently? So the other one was older stuff. More recently, we worked on the Landau Hamiltonian. So it's, as I said in the beginning, two-dimensional fermions. I mean fermions in R2, and a magnetic field, a constant magnetic field perpendicular to this plane. Okay, this is but still non-interacting fermions. This is standard Hamiltonian that is studied. The constant magnetic field. So this little a is called a gauge, and you can explicitly write down a gauge. So this is here a of x. So if you know this thing, then this is of course very familiar, and you can spectrally decompose this Hamiltonian. So the eigenvalues are b. B is a number, positive number, say, times 2l plus 1. So it's like the natural numbers in steps of 2, multiplied by, maybe I have a picture. So, okay, so this is a picture by, so it's two-dimensional fermions in RT. So this is the, okay, so here's the rotation. Dx1 of the second component of the A field minus the second derivative of the first component is equal to B. That's how these two things relate. And the spectrum of H is very different from the spectrum of the Laplacian, say. You have points. These are the eigenvalues, and they are infinitely degenerate. The eigenvalues are also called Landau levels. So the spectrum is very different. Okay, for those who are familiar. You can, so that's the spectral decomposition. PL are the eigenprojections. They depend on the what is called Landau level index. L goes from 0 to infinity. That goes through all these eigenvalues. And the projections are explicit. So there is a Gaussian decay and some non-translation invariant part. So that's the red part. Unlike, I mean, they're not translation invariant, there is magnetic translations, but, and in front there is some prefactor, which is Laguerre polynomials, but it's a polynomial times an exponential. Okay. So I'm only talking about the one particle picture. So you have to say at temperature zero, and the Fermi projection, well, you give me some mu. Mu is like the edge of, I mean, the Fermi level, and you consider all eigenvalues below mu. So that is the Fermi projection. You project, you take the first, say here it's the first two eigenvalues into account, or the first two eigenprojections. Okay. So this describes the infinite volume ground state, right? And then you do the same game. So again, written here, never mind all this. So the ground state is local, and then you do the localization, as we did before, by multiplying the Fermi projection from the left and right with the indicator in position space. So that's localizing the Fermi projection. And then you have the same concept as before. You look at the local entropy. And the entanglement entropy, as we know, is just twice this factor. But it's sufficient to look at this local entropy with the same function, with the same entropy function, von Neumann entropy function as I had before. And you look at how does this function now behave if you blow up the domain to which you localize. The very same thing, and it turns out to have a true area law scaling. So the entropy behaves, so it scales with L times the boundary. So it's a true area law. There is no log, and the log is okay. There is no log because there is no log and a certain coefficient. It depends on the root of the magnetic field and the length of the boundary curve. We are just in R2, so it's right, and a certain coefficient m, which is a bit more complicated, but it only depends on the Landau level, on the last Landau level.
And again, a stupid question now. Suppose once lets B go to 0.
Yeah. Then no.
There's probably
case,
I guess.
Now, in this case, it's not. So that's right. In this case, it does not go to the. It does not develop a singularity.
But then this term is out. But then on the other hand, there must be this logarithmic term.
Yeah. In this case, you have to be a bit careful. If you so so B going to 0, you also have to let the mu go into infinity. Mu to 0 is too singular.
Sure, of course, because you get more and more particles. So
exactly. You have to do a joint limit, but it's. But still, not necessarily. You wish. I mean, it's the first question. Oh, it's one of the questions you want to understand. It's not what happens as B goes to 0, but you have to also do something with the mu, and that's not yet decided. But it's not obvious that there has to be a log. The two models are maybe too singular or too, in one case you only have the discrete infinite volume projections. And on the other case, you have absolutely continuous. It's quite different, but maybe there is, but it doesn't have to. So what I say, if you're just looking at the lowest Landau level, so the Fermi projection to the lowest Landau level, this asymptotic behavior was known in physics. Let me say, so this was in physics. By Rodriguez. So where is my list? Okay, so by Rodriguez and Sierra. So they 2009. So 10 years ago, they found this formula. I mean, it's a physics paper. I mean, there's nothing rigorous, but I admire it for guessing the right result. Right. No, it's an inspiration. And if you look at it, I mean, they came up with the formula. So this is nice. And there is a proof by Charles and Etienne 2 years, or this appeared this year. They use completely different methods, also about the Fermi projection onto the lowest Landau level. And we have a proof and a new formula for all Landau levels, because it's more complicated, because Landau levels mix at higher Landau levels mix at this leading order. But I will not say anything about the proof, but these two models are different. So just the free Laplacian in the ground state has a log, an extra log. The Landau level does not. I mean, for the Landau Hamilton, you don't have a log term. And the maybe I have some comments here. Let's see where this is. Landau Hamiltonian. Let me get a second. Okay. Yeah, here it is. So we talked about the b equal to 0 case. We had a logarithm, but the decay of the Fourier transform of the indicator function is very slow. In this case, we have for the Landau levels, the projections have an exponential fast decay, and therefore you don't have a log. Other explanations are that you have a gap, so the eigenvalues are separated, and therefore you don't have a log. Okay, so from my point of view, I'm through and happy to answer questions.
Great. So first of all, thank you very much for this nice talk. So
It's a pleasure.
And let's open the discussion. So I mean, if you want to ask a question, just unmute yourself and go ahead.
Yeah.
And of course, I have like many questions. What I would really like to understand is how you compute this area, the way you always said this is this very complicated prefactor.
Yeah.
Which you compute somehow with methods of pseudo-differential calculus, if I understood this correctly. I mean, could you give an indication on how this works?
So it comes from, so the origin is Schege asymptotics. So Schege asymptotics, you take Toeplitz matrices. Toeplitz matrices are ones that are constant along these diagonals.
Mm-hmm.
Right? So you take the infinite, say you take the infinite volume one, and then this is an old topic. You take a chunk. I mean, you take an n cross n times n submatrix, and look at the determinant,
mm-hmm.
and ask how does the determinant behave as n goes to infinity? And the elements in these diagonals are the Fourier transform of a certain function. This function is called symbol. And if this symbol has, if this symbol is smooth, then you have an asymptotic expansion that goes like n or and order 1 and so on. But if the symbol is discontinuous, then you have, then it's not the standard one, but you have an extra log n, right? So these operators, say the Laplacian, they are a continuous version. So the continuous version of these Toeplitz, of this, so to say, discrete ones, are Wiener Hopf. That's just the name for the continuous version of Toeplitz. So if you take, and in this Toeplitz, for this Toeplitz matrix, there is a description how you get this coefficient. And now you have to translate this to the continuous case. I mean, other people have done this too. Katz, for example, in the 50s, he found probably a formula in the continuous one-dimensional case. And it was an ingenious, feat by Widom to come up with a multidimensional version, a formula for the multidimensional. And I asked him once, how did you do this? And he said, I have no idea. It's okay. So that's one thing. So to
generally, you always consider the determinant and.
Well, the determinant is one thing. The determinant, so the determinant, the determinant of this matrix, you can write as the trace of, or the log of the determinant, you write as the trace of the log. Okay? The log of this function. Okay. So now the log is replaced by other functions. Okay? And this other function in our case is the entropy.
Okay, so this little h.
This little h, right. So typically in tuplets, they deal with the determinant. And you just write it as a trace of the log. And we are interested in h, in this function h being the entropy function, ultimately.
Okay.
Yeah. Okay.
Okay, I think, well, of course, we have to look at your papers in more detail anyhow. So,
yeah,
Claudio?
So I have a question. What is the symbol that you're looking at exactly?
The indicator function. The indicator function.
Okay.
Okay.
So it's just basically.
Yes. Yeah. Exactly. Yeah.
Okay.
That is this community that is called the symbol.
No, but well, I mean, symbol. I mean, there's many symbols that one can choose for different operators, right? I mean, that's just.
Yeah, but I mean, so take a tuplets matrix. So you have this coefficients that are constant along the diagonal. So this coefficients may be the Fourier transform of some function. Okay, and this function is in this business. The function is called symbol.
Okay, fine.
Okay.
How is that related to other notions of symbol, like in the Wigner-Weil quantization and so on?
Also, that's also related.
That's the same thing, or is that?
It's more, yeah.
Okay.
So this means also if you take a differential operator, it's just a polynomial, isn't it? I mean, this is how it works.
Well, these are not polynomials.
No, of course, here not, because you don't consider all the solutions. We have to cut this out, cut something out.
Yeah, but to prove the asymptotics, let me see. So where do I state something? Let's see. Let's see. So if I look at say the trace of h of something, okay. So typically you prove this first. So this function, you replace this function h by a polynomial or even a monomial. So in order to prove asymptotic results, you don't start typically with the difficult entropy function, but you do it first for polynomial. So you compute moments.
Okay, this sounds. I mean, this
so
sounds.
From moments. So this is the typical strategy in many cases. So you do it for moments. So the first non-trivial thing is h being a square function in a second order polynomial.
Yes.
And then you go from polynomials, you go to continuous functions that are nice on the two endpoints for some reason. And then, and then you go, somehow you have to go from this nice functions to the entropy function where you have a problem at the 2 bound points because they are not differentiable. That's another topic. I mean, it's there you use this Biermann-Solomyk bounds.
I see.
This is a difference. So one thing is you do asymptotic analysis for h being a polynomial. So you compute this moment, you compute asymptotics of moments.
Yes.
Yeah. Right. And then, so if you're just a mathematician, there is not really a reason to go to the entropy function because maybe you don't know about it. So you would do it for polynomials, and you say, well, for nice, say analytic functions, that's what you have, and that's where you would maybe stop. But then somebody comes to you and say, well, does this asymptotics also hold for the entropy function? And the answer is yes, at least to the leading asymptotics that I'm interested in. And there is an asymptotic expansion maybe to lower order for nice functions, but you're never sure that you can plug in your entropy function.
Sure. Mhm.
Yeah. Yeah.
Okay, very good. But maybe just another question. I mean, now, do you know if anything has been done for the Dirac equations, or if you?
No, I don't. No, I don't.
Let's say you consider a static system of relativistic fermions, and then again you take a certain ensemble of them, non-interacting. Do you know if people have looked at this question?
There is, I mean, there is in high energy physics, I see sometimes Ryu. Have you came across Ryu? As I mean, RYU.
I see. So
I haven't done, I don't understand that. I mean, I have to say, many people, I mean, in the physics community, many people work with what is called the replica trick.
In fact, I learned this once as a student, but I never really understood it.
It's a non-rigorous thing. I mean, it comes with it comes as follows. I mean, if we look at moments, so if I replace the little h here by a function t to the n.
Okay, so just integers, and then you have this.
Yeah, integers, and the replica comes by replicating this operator n times. And they do. I mean, but it's never rigorous. They get results for sure. They can deal with that. I can't, and it's never rigorous. It doesn't have to be. I mean, I don't mind, but it's not rigorous mathematics. That's
okay. Sure.
That's
well, also probably the result can be trusted, I guess, but it's not a proof.
It's not a proof. Trusting is, you know, yeah. If you only trust numerics, say it's not so easy to detect the logarithm.
Sure.
So I mean, these computational physicists, I mean, they're good at it, but I mean, this conjecture, I mean, this formula that I printed here, I mean, this was not found by numerical, by computational physicists, but by one mathematician, one theoretical physicist. So you don't easily guess this. Yeah.
Okay, great. Are there other questions? Anything else we should discuss? Well, apparently not.
Oh, just sorry. Just a really naive question. And maybe it doesn't even make sense, but is the entanglement entropy? Can I understand as a sort of measure of how entangled the system is? Or
Yeah.
Okay, so that's kind of the motivation of that.
This is the motivation. So you have the big system. You cut it. You localize it, and then you want to know how are those particles in this lambda correlated with the outside.
Okay, and so an increase in entropy, does that correspond to a decrease in entanglement, or
right, decrease in
okay,
yeah,
okay, all right. So then the question wasn't that naive at all.
This is one measure. I mean, there might be other measures. I mean, it's just, you should not forget, this is just one number.
Yeah.
And the number one single number can never describe the whole state, because
sure. Yeah, but it gives a simple feature of it.
I mean, you cannot just judge a single researcher by one number. And you cannot, I mean, it's the full state describes the state. Yeah. Not just a single, and but entropy has been a useful number for measuring information or lack of information. It's not the whole thing.
Yeah, but it's correlated, and
it measures correlations. It's not the only one. It's one.
Yeah. Okay. Thank you.
Yeah, sure.
And in fact, I also have a very naive question, so which might be stupid.
You know, Felix, let me interrupt you. Let me interrupt you. I'm participating in this IAMP One World Seminar.
Mm-hmm.
You know this, and they also record these talks.
Yes.
And they stop recording and say, now are the silly questions allowed? And then it becomes interesting.
In fact, I can still decide later what
because then it's actually, they talk about how, and I like this actually. So if you don't want to be, I mean, I don't mind. There are no silly questions, only silly answers. Okay, please, Felix.
Well, so what I would like to know, I mean, like talking of entropy, you always have something like a second law of thermodynamics in mind. So entropy should increase in time. Are there also some kind of monotonicity statements? Does this even make sense in the context of entanglement entropy?
Sure. I mean, there is something studied. I mean, there is no dynamics here, but it goes under the name of quench dynamics. So they start with some equilibrium state, they deform it, and then they let it run. Well, they take some equilibrium state and they time evolve it with another Hamiltonian. So it's not a stationary state, and so you have and then you can look at the time evolved localized entropy or local entropy, and you can look at how does it as t goes to infinity and the domain becomes large. So this has been this has been studied. What it has to do with the second law, I don't know, but you can look at. I don't know whether this is exactly what you asked me, but.
Well, somehow, yes. So in this case, then the time direction is determined by the fact that you start from an equilibrium state and then you move out of this state by the time.
Exactly. You can start, yeah. Right.
But then build on Mort's question, basically, if the entanglement entropy increases, that would mean that the actual entanglement decreases, right? So or the other way, or what was the direction?
So zero entropy means that you have all information, maximum information. Okay. And high entropy means that you have low information.
Okay, but so entropy should be increasing, but then what does this tell us on the entanglement? Is the entanglement increasing or decreasing?
Yes, increasing.
Okay. So if you have an open system, so to speak, it will get more and more entangled.
Yes.
With the surrounding. Okay.
Which I have to be honest is not as trivial to accept.
Why?
I mean, why? Because say you have a domain, and you want to know the correlation between this domain and its complement. Well, the complement is pretty big, so now you increase it. The complement still is pretty big. So why does it actually? It's not. I mean, I know it is true, but you also have to be a bit careful. It's not. We're not saying that it is monotonic. So it does not say, and it's probably not true. So you have one domain, and you have a domain which is bigger. It does not mean that the entanglement is, or that the entropy is bigger. So they are not monotonic because it goes with the boundary. The boundary is pretty, if it's wild, then it goes with the length of the boundary. It can be larger.
Mm-hmm. Yeah, I was more interested in the time evolution case when you take a fixed area, and you look at the entanglement entropy. You would expect an increase in entanglement, right?
Yes, right.
In time.
Yes, I would.
So this could in fact, so this would sort of correspond to the second law, no?
What is the second law?
well, I mean that the entropy. So if you have this fixed domain, it evolves in time. It gets stronger and stronger. It gets more and more entangled with the rest of the universe, so to speak.
Mm-hmm.
Then basically the entanglement entropy should be increasing along with time, right?
Yeah. So
and so that's so you get the increase of entropy, so to speak. In that fashion.
So one person that did a lot in this area from a theoretical physics point of view is Calabrese. Maybe you came across that one. So there's an Italian group, but it's mostly on replica. I mean, there's also in Germany Ingo Peschel, mostly in one-dimensional, and there is in England. What's this guy? He's in Oxford. I don't know.
Well, don't worry.
Yeah, I've been more my approach. This is more thinking in terms of Fröhlich's approach to quantum theory. Are you familiar with that? His ETH stuff?
Well, I grew up in Vienna with the Turing school, and I guess they are not pretty. I mean, they are quite similar. I mean.
Okay.
Yeah.
Okay. Well, maybe that's a good point to stop. That all questions have been answered, and well, Wolfgang, I'll come back to you. Well, we'll get back to you with more detailed questions.
Sure.
Okay, so then thank you very much again.
It was my pleasure.
It was great that you were here. Well, and then I wish everybody a nice weekend and see you again soon.
Yeah.
Thank you.
Thank you. Bye-bye.
Yeah, have a nice weekend.
Bye-bye.